we're going to start on page 10. We're going to skip all the way to page 10 because 1 through 9 we kind of covered through the videos and through your lecture recordings from last week. Remember, we had snow days, so we covered 1 through 9. We went over the reaction quotient on Tuesday, and now I want to go over one more reaction quotient problem before we go into new territory, and that new territory is the ice table. Right now, this should be a review of a concept that we originally talked about on Tuesday. And I got the recording set. Hopefully everything will go well today. All right, so just as a reminder, we're going to call Q the reaction quotient. Okay, and we will compare it to K. It's basically used to compare the number Q, the magnitude Q. Its number is, without units, these are all unitless entities, is being compared to K, which is the equilibrium constant. All right, let me see. Right, so are we at equilibrium? Yes or no? If we are at equilibrium, then Q is equal to K. Now this equilibrium constant you'll get from a textbook, or I'll give it to you on an exam. Every reaction will have its own equilibrium constant, provided it is an equilibrium reaction. Question is, are those concentrations enough for it to satisfy equilibrium, products over reactants? If not, it's going to shift a certain way. It's going to shift a certain way, kind of like Le Chatelier's principle, which is what we covered in our last lab. So we're going to put Q first. Okay, we will put Q first. Where do the alligator jaws point?
I think we did cover this problem.
We did this?
On the videos. Yeah.
Oh, it was on the videos?
This one, yes.
Oh, okay. All right, then what I'll do, Maria, is I'll just go over the basic concepts, and then we'll go over the ice table. So thank you for that. It'll just save some time. Now that I think about it, maybe it was, you're right. So if Q is greater than K, where will the reaction go? Are we at equilibrium? No, but where will the reaction go to get to equilibrium? Okay, so not at equilibrium. We'll go shift towards the reactant side. Okay, if Q is equal to K, we are at equilibrium. And if Q is less than K, we're not at equilibrium. Where do we go to get to equilibrium? Okay, the alligator jaws are pointing towards the product side, so we're going to shift towards the product side. All right, to do this, to make sure that we're getting the right answer for any quiz or exam or future chemistry, MCAT or whatever, we have to put Q first. So this is called the gator rule or the alligator rule. All right, so we had a problem that was on the video. Just one thing before I go, and thank you again for saving us some time here. We want to put concentrations. Okay, concentrations. Okay, concentrations go into the equilibrium. Not moles. Okay, so what's the concentration of Cl2? We take that 0.0083 and divide it by 2 liters, okay, which is 0.00415. Big M. Okay, so it is this that goes in here. Okay, it's this that goes in here, not moles, but moles over liter goes in here, because this is a mistake I see on the exams. Okay, so something like this on the exam, but what goes in here is moles over liter. Okay, am I making sense? They don't just put 0.0083 here, it's 0.0083 divided by 2. Moles over liter is molar. The second mistake I see with students is that you forget that there's a 2 in here and products over reactants. So what does that make that in the equilibrium expression? Squared. Okay, there's a 2 here. When you balance it, what will that make the NO here? Squared. Okay. All right, so those are some of the things that you need to look out for when you do this type of problem on the test. All right, so we'll have a review before the test time. For now, we'll go on to some new material, and that is the ICE table. So this is something I'm pretty sure was not covered in the videos, and now we'll cover it now. All right, a lot of students have trouble with this, and they go to the tutoring center and whatnot. So let's see if we can get this right, the concept known as the ICE table. All right, so ICE table. Okay, the I in ICE stands for initial. The C in ICE table stands for change. And then the E in ICE table stands for the final equilibrium. Okay, so this is what we're going to call an ICE table. Okay, when do we use an ICE table? Okay, we use an ICE table when we want to determine the final equilibrium concentrations. Okay, the final equilibrium concentrations. All right, so let's do a problem here, and something like this will be on the exam. All right, so I will put some stars here, so make sure we know how to do this. All right, so starting with an initial concentration of 0.040 molar initial, what is the equilibrium concentration of HI, H2, and I2 at equilibrium? Okay, according to this equation. Is this an equilibrium? Yes or no? Okay, looking at the back and forth arrows, the answer is yes. Okay, it is an equilibrium. Okay, so we have H2 plus I2 going back and forth and settling with HI. Now, let me just try to explain this to you. Okay, so imagine you have a bottle of HI. Okay, imagine. Now, you know, Jacob and the rest of the class, this is an equilibrium. So this bottle does not contain HI. Okay, it's an equilibrium. What else does this bottle contain? This bottle also contains H2 and I2. Okay, because it's an equilibrium. So some of this HI will go back. Some of this HI will go back because remember, it's in equilibrium. So when it's all said and done, how much of it goes back, how much H2, I2, and HI will be there, we're going to use an ICE table to find out. Right? So this is what you'll do in the exam or in the future if you ever encounter this ever again. Okay, I'll rewrite the equation. So ICE. Okay. So here initially we have 0.040. Initially here we have 0. Initially here we have 0. Okay, remember this is initial, this is change, and this is equilibrium, final equilibrium concentrations. Okay, some of it will go back this way because some of it you can't have 100% this or that, it's in equilibrium. So some of it will go this way, so the reaction is going to shift this way. It's going to shift that way because initially you have 0.040. That's not finally. That's not your equilibrium. So it's going to shift this way. Minus not x. Okay, it's going to be minus 2x. Why did I say minus 2x instead of minus x? Because of the coefficient. Excellent. Good job, Bailey. Because of the coefficient. This is going to be minus 2x. Okay, what will this be? It's going this way, it's shifting left, plus 2x. Okay, what's the coefficient here? 1, so it's going to be plus x. And this will be plus x.
So the change for H2 and HI are basically plus x, correct?
Why? Because what's the coefficient? It's just a 1. Okay. So at equilibrium, this will be x, x, and 0.040 minus 2x. Alright, so now we have our equilibrium concentrations. So we set up the ice table. Number 2, we'll plug into equilibrium expression. What is the equilibrium expression here? Products over reactants. HI. What is HI? What do we need to do with that? Not multiply by 2. Square it. Very good. Times H2 times I2. This is products over reactants. Okay, no solids, no liquids. There's no solids and liquids here. All right, so this is 48.8. All right, so let's plug in 48.8 equals 0.040 minus 2x whole squared divided by, what's the equilibrium of H2? X. What's the equilibrium of I2? X. Alright, so I'll just do some cleaning up. Okay, X squared. Alright, so now we will solve for X. This is how I want you to solve for X, okay? You'll do this on the exam. Okay, you'll take the square root of both sides of the equation. Okay, to solve for x. Square root. Square root of 48.8, what is that on our calculator? Is that 7? Square root of 49 is 7, so. Come on. I can't find the square root button on my calculator. 6.9? Yes. Oh, here we go. 6.8, okay, yeah, 6.9. We'll do 6.9, yeah, you're right. 6.9. The square root of 0.040 minus 2x whole squared is just 0.04 minus 2x. And the square root of x squared is just x. All right, now we'll solve for x. Can we do this math? And now this just becomes algebra. So I'm going to multiply both sides by x. 6.9x is equal to 0.040 minus 2x. Okay, everyone see this? Okay, I'm going to move the minus 2x to this side of the equation. Everyone okay with the algebra? This is algebra, not chemistry. 6.9 plus 2 is 8.9x equals 0.040. So x is equal to 0.040 divided by 8.9. And what is this on our calculator? 0.0045 molar. Okay, don't forget the units. 0.0045 big M. Okay, big M. All right, so this is x. We solved for x, but what is x? Okay, what is x anyways? X is, what is x? Okay. X is this, which corresponds to the concentration of H2. X is this, which corresponds to the concentration of I2 at equilibrium. And 0.040 minus 2x, minus 2 times this, is the concentration of HI. So we're going to plug this x back in here. Plug this x back in here. So our final answer is at equilibrium. This is what you'll put on the test, okay, at equilibrium. The equilibrium concentration of H2 is equal to X, which is 0.0045 molar. The equilibrium concentration of I2 is X, which is 0.0045 molar. And the equilibrium concentration of HI is 0.04 minus 2 times this x. Minus 2 times this x. Everyone see that? And what is this on our calculator? .031 molar. So this is the answer that you want to put on the test, okay, or when you get a similar problem. Okay, so this is our answer. So I have something to tell you guys, and what I'm going to tell you is that you should be able to get this answer correct on any exam. How? Okay, there's a way to check your answer. How can you check your answer to make sure this is 100% or at least close to 100% the right answer? If these are the equilibrium concentrations, what can you do? You plug it in and it should equal what? 0.8. Okay, so excellent. So we should be able to plug it back in to get our answer, recapture our answer, because these are the equilibrium concentrations. Plug it back to the equilibrium expression to get the equilibrium constant, which is 48.8 at this temperature. So let's check our answer. Okay, so we'll plug back into the equilibrium expression. Which is the concentration of HI squared divided by the concentration of H2 times I2. So HI squared, we found it to be 0.031. Don't forget to square it. Okay, don't forget to square it. Divided by H2. H2 is 0.0045. Concentration of I2. What's the concentration of I2? 0.0045. Okay, and what is the answer when we get that? We plug it in. Okay, 0.031 squared divided by 0.0045 times 0.0045. 47.5. I think that's close enough. Okay, with all the rounding and stuff. So I think that's good enough. Okay. So, yeah. All right. So this is somewhat like you'll see on the exam. You'll take the square root of both sides, solve for x. First of all, we'll construct our ice table, plug it into the equilibrium, solve for x, and then plug it back in to make sure our answer is reasonably correct. I would say these concentrations are reasonably correct, and this is a reasonably correct answer. Okay. All right, so can we do this on the test that's coming up after spring break? All right, so make sure you study this. All right, we have one more ice table problem I'd like to show you guys. Half of it will be on the exam. The other half, the math portion, will not. The math portion will not be on the exam. So just by a show of hands, how many of you know the quadratic equation? 1, 2. Go ahead.
I know I should, but
you know you should. You should.
I said I know I should, but I was just saying, I was like, my brain is blanking out right now on me.
Okay, so no quadratic equation on the exam. This ice table problem requires the quadratic, but there's no quadratic equation, so you will not have to know the math. I'll do the math, but you don't have to do the math on the test. The only math that you'll have to know will be from this type of problem. Okay. All right, so this is kind of a hard one. It's a little difficult one, so we'll go ahead and do it together. But like I said, there's no quadratic equation on the test. Okay. So let me just go ahead and get my notes for this one. Quadratic equation. All right. Are you guys ready? Want to do this problem? Okay. All right, at 1280 degrees C, the Kc for the reaction Br2 goes back and forth to Br. Is this in equilibrium? Yes or no? Yes, look at the arrows. Okay, the equilibrium for this is 1.1 times 10 to the minus 3. If the initial concentration of Br2 is that, and the Br is this, calculate the concentration of these species at equilibrium. Okay, so let's just rewrite everything. So they tell us decay here is 1.1 times 10 to the minus 3. So the first thing we'll do is we'll plug in these concentrations. And if we plug in these concentrations, what should it equal to? Okay, so the equilibrium for this is Br. What should we do with that Br? Square it divided by Br2. Okay. So let's plug in the concentrations here. What is the concentration of Br? 1.1 times 10 to the minus 2, so that's going to be 0.012. Okay, what should we do with that 0.012? Square it. Divided by the concentration of Br2. What's Br2? 0.063. What should we do with that? Okay, raise it to the 1 power. And this should equal to 1.1 times 10 to the minus 3. Should equal to 1.1 times 10 to the minus 3. All right. Everyone get this step here? So let's see if it does equal to 1.1 times 10 to the minus 3. So what's 0.012 squared? Divided by 0.063. Huh? What? 0.0023. It does not equal to 0.0011. So what has happened here? Are we at equilibrium? Yes or no? We are not at equilibrium. So, which way will the reaction shift to get to equilibrium? Alright, we're going to put Q first and compare it to K. K, they tell you in the problem, is 1.1 times 10 to the minus 3, or 0.0011. What is Q? 0.0023. So which is bigger, Q or K? Okay, Jacob, very good. So which way will the reaction shift? Okay, we are not at equilibrium. Okay, where will the reaction go though? Okay, it's going to shift left towards the reactants. Okay, so this is going to shift to the left. Okay, so now let's do our ice table. We'll do our ice table now, knowing that this reaction is under these concentrations are going to the left. Okay. Okay, so ICE. Okay, what is the initial concentration of BR2? .063. What is the concentration of BR? 0.012. Which way did we say this is going?
Shifting to the left towards reactants.
Okay, it's like we said before, shifting left. So this is going to be not minus x, but minus how much x? Minus 2x. And this is going to be what? Plus x. Okay, so at equilibrium, this will be 0.063 plus x, and this would be 0.012 minus 2x. Okay, minus 2x. Alright, so just as we did before, okay, first of all, we use the Gator rule, step 1. Okay, to determine where it's going to shift, left or right. We found out it shifts to the left. Number 2, we set up ice table. Okay, making it go to the left. And then number 3, we'll plug into equilibrium expression. Alright, so what is our equilibrium expression? It's going to be BR squared divided by BR2. Just as we wrote here. So at equilibrium, BR is going to be 0.012 minus 2x. What should we do with that? Square it. Everyone see why we square it? Okay, divided by, what's the equilibrium of BR2? 0.063 plus x. Okay, what does all of that have to equal to? What will this have to equal to? The equilibrium constant. But what is the equilibrium constant? Times 10 to the minus 3. 1.1 times 10 to the minus 3. Okay. So here we're going to solve for x. Okay, this is step 4. So from here on out is the quadratic equation, so it's not going to be on the exam. Because some students may not have had the quadratic, or maybe forgot, whatever it may be. So we're going to solve for x. And first of all, what we're going to do is we're going to take this 1.13 times 10 to the minus 3 multiplied by 0.063 plus x. So this math is not on the exam. Okay, this is going to equal to 0.012 minus 2x whole squared. Okay, I'm going to expand this. A minus b whole squared is a squared minus 2ab plus b squared. Okay, I'm going to use the distributive property on this. And then ultimately, okay, we'll just skip a bunch of steps here. Okay. So I'm going to get it into a form that's into the quadratic. Okay, when I put it into the quadratic form, okay, this simplifies to 4x squared. Again, this is not on the exam. Minus 0.0491x plus 7.47 times 10 to the minus 5 is equal to 0. So this is just a bunch of steps, okay? Okay, so this goes into the quadratic equation. Okay? You guys remember the quadratic equation? Okay. Anybody remember the quadratic equation? Okay, very good. Good job. Okay. So to solve for x, we'll plug it into the quadratic. Okay, minus b plus minus square root of b squared minus 4ac, all of that divided by 2a. All right, so this is the value of x. Okay, so what is minus b? Okay, minus b, this is our b, so that's going to be point, minus into minus is plus. It's, again, this is not on the exam, but this is going to be 0.0491 plus minus b squared. What's b squared? It's going to be this squared. When I square it on my calculator, I get 2.41 times 10 to the minus 3 minus 4a. What is a? Is 4. C. What is c? 7.47 times 10 to the minus 5. All of this divided by 2a. 2. What is a? 4. Okay, so when I do that, I'll get 0.041491 plus the square root of all of this divided by 8. And then I'll get, that's one answer. And then I'll get another answer, which is 0.0491 minus, okay, minus the square root of this minus all of this divided by 8. And I'll get two answers. Okay, one answer, when you do this plus, the plus will give you 0.0105 big M. Okay, the minus will give you 0.00178 molar. So you're going to get two answers. Which answer is right?
Wait, is that 0.00178?
Yes. Okay, putting it into the quadratic. All right, so which one do we choose? Because we get two answers. One when we do plus the square root of all of this divided by 2a, which is 8. And minus square root of all of this divided by 2a, which is 8. Okay, so to figure out which one we throw out, we're going to plug it into the ICE table. Or plug back into ICE table. All right, so what's the equilibrium concentration of Br2? What is the equilibrium concentration of Br2? It's going to be 0.063 plus X. Okay, so let's test out 0.0105. So 0.063 plus this X. And I'm getting 0.074 big M. Okay, what's the equilibrium concentration of Br? Okay, that's going to be 0.012 minus 2x. Okay, what is x? Okay, we're testing out this one. That's going to be 0.0105. And when I do that on my calculator, I get something very strange, okay? I get a negative 0.009 molar. So can you have a negative concentration? Okay, so this one we throw out. Okay, so this is not the right answer. After the quadratic, we get two answers. Okay, this one, when we plug it back into the ice table, we get negative, and we all know there's no such thing as negative concentrations. Okay, so we're going to test 0.00178, and this should be the right answer. Alright, let's do the same thing. BR2 is going to equal to 0.063 plus X. 0.063 plus 0.00178. And I get 0.065 molar as my equilibrium concentration of BR2. And then my equilibrium concentration of BR is 0.012 minus 2x, which is going to be 0.012 minus 2x. We're testing 0.00178, right? Minus 2 times 0.00178. And this is going to equal to, on my calculator, 0.0084. 0.0084. Okay. So these are positive, and this should be my right answer. Okay. So how do I know it is the right answer? How can I be 100% sure? What can we do? Okay. Plug it back into this. Very good. And what should it equal to? 1.1 times 10 to the minus 3. Okay, should be reasonably close. All right, so let's just plug it back in to check our answer. Okay, so it's going to be K is equal to BR squared divided by BR2. Okay, let's check our answer. So BR2 is 0.065. What's BR? 0.0084. Okay, thank you. Very good. Square it. And what should it equal to? 1.1 times 10 to the minus 3. Alright, let's check this out. 0.0084 squared. .001. Yeah, it works, right? 1, 2, 3, yeah. 0.0011. It worked. It's correct. .00108. 0.0011. Yeah. Okay. This is the right answer. So this is how you do a little bit more difficult ice table problem where you have to do the quadratic. Okay? But you will not have the quadratic on the exam. All right? This is something I can assure you. All right. All right. So check out this problem. Okay? How long it took. One whole page, and then another whole page. Anyways, this is the right answer, And this is how you use the ice table. All right, so as I said before, okay, just up to here. Okay, just up to here. In terms of the math and the ice table, you can use and focus on this problem that has the 3 stars by it. Alright, so we did 2 ice table problems. Okay, this is the one again I'd like for you to focus on. And then this is the last bit for chapter 14, I believe, and that's Le Chateliers principle. Since we had a lab on it, now I have an opportunity to explain the lab that you guys did last Monday or last Tuesday, okay? Day before yesterday or on Monday of this week. Right, so let's go ahead and knock this out, and then we'll end class. Anybody have any questions? The last part of this chapter, then we'll do a review. Okay, any questions or comments? Okay, got about 20 minutes. Yeah, 20 minutes. All right, so Le Chateliers principle. This was our lab that we did on Monday and Tuesday. And Le Chateliers principle has to do with an equilibrium. So, it's an equilibrium. Here's another equilibrium. But in Le Chateliers principle, we disturb the equilibrium. We disturb it. Okay, you disturb the equilibrium. How can you disturb an equilibrium? There's 3 ways. Okay, there's 3 ways to disturb an equilibrium. So 3 ways to disturb an equilibrium. Okay? In other words, the way we disturb it is we add an external stress. Okay? We disturb the equilibrium. So what will it do? The equilibrium adjusts itself. Okay? If I push you, you push back. Okay? In such a way that the stress is partially offset as the system reaches a new equilibrium position. So we disturb an equilibrium. What will the Le Chateliers principle do? It will offset it. Okay, so this is the key word I'd like for you guys to know, offset. Okay, how do you offset the disturbance? Okay, you do the opposite. Okay, offset the disturbance. So how do we disturb an equilibrium? Okay, there's 3 ways. Okay, 1, you change the concentration of products or reactants. So you add or you remove products or reactants. Add or remove concentration of products or reactants. You change the concentration basically. Okay, you change the concentration. Okay, the second way you disturb an equilibrium and the equilibrium offsets itself according to Le Chatelier is, this is for gases now, you increase or decrease the pressure. When we talk about pressure, we're really talking about gases. So this applies for gases. Okay, here we're talking about in step rule 1, changing the concentrations, moles over liter, products or reactants. And then the third thing we can do to disturb an equilibrium, which the Le Chatelier principle will offset it, is by increasing or decreasing the temperature. So this involves whether the reaction is exothermic or endothermic. So these three things, what happens is that if you add or remove a reactant or product, the equilibrium will change. It will offset. It will remove that disturbance. If you increase or decrease the pressure, in terms if you have a bunch of gases in there, the equilibrium will offset. Okay? It will offset that increase or decrease. If you increase or decrease the temperature, depending on whether it's exothermic or endothermic, the equilibrium will offset. Okay, we'll do the opposite. Okay, a lot of people, or the way I also teach this is that the equilibrium, when I say offset, it will do the opposite of what you do. It will do the opposite of the external stress. All right, let's look at condition 1 here. Okay, you add or remove a reactant or product. You change the concentration. Okay, changing the concentration. Okay, this is situation 1. This is scenario 1. Okay, changing the concentration. Okay, so what happens if I add NH3? Okay, what will the reaction do? Where will it shift? Will it shift to the side that has more NH3? After all, you added it. Or will it shift to the side to offset and remove that NH3? Okay, what will it do? If you add NH3, it doesn't make sense for the reaction to make more NH3. What will it do? It will go to the side that will remove the NH3 that we added. So if we add NH3, where will the reaction shift in this equilibrium? It will shift left to the reactant side. Okay. What happens if I remove NH3? Where will it go? It will shift right to the product side. Okay, what happens if I add N2? Where will the reaction shift? You add N2, the offset, what's the offset? If I add N2, what's the offset of adding N2? Removing N2. So which way will the reaction shift to remove the N2? To the right. Okay, what happens if I remove H2 gas? Okay, what is the offset of removing H2 gas? The equilibrium will react in such a way to add back the H2 gas. So where will it shift if I remove H2? To the right or left? To the left. Okay, so whatever you do, it does the opposite. Okay. If I add a product, it will shift to the reactant side. If I remove a product, it will shift to the product side. Add a reactant, shift to the product side. Remove a reactant, where will it go? To the reactant side. Okay. So that is what happens when you disturb an equilibrium. How will it react? Okay. It will offset it. Okay. So that's changing the concentration. Okay. Everyone understand this? Okay, increase the concentration of product, it's going to shift to the left, removing the product. Decreasing the concentration of the product, it's going to shift to the right to increase it. Increasing the concentration of the reactant, it's going to shift to the right to decrease the concentration. Yes, it's going to shift to the right to decrease it. Decrease the concentration of reactant, it's going to shift to the left to increase the concentration of the reactant because you decreased it. Okay, this is the idea behind the offset. All right, so that is one way we disturb the equilibrium, changing the concentrations. All right, the second one is a little confusing because it involves increasing or decreasing the pressure, and it involves gases. All right, so this is the second condition in which we mess up the equilibrium. All right, so scenario 2 is we change the pressure. Okay, what does this apply to? What state? This applies to gases. Okay, so if you see gases anywhere, you have to be, extra cautious. Okay? Because you can not only change the concentration of the gas, but what else can you do? You can change the pressure of the gas, either increase it or decrease it. All right, look at this equation here. All right, I am going to increase the pressure of this reaction. Okay, I'm going to increase the pressure. So what is the opposite? So this is the disturbance. I'll put it here. Okay, this is what we do to the equilibrium. Is this an equilibrium? Yes. Okay, it's in equilibrium because of the back and forth arrow, right? I'm going to increase the pressure. Okay, what is the offset of increasing the pressure? Okay, what's the offset or the opposite of increasing pressure? Decreasing pressure. Okay, so which side in this reaction? Has decreased pressure? The one with more moles or less moles? Less moles. So which side has less moles in this one here? Product side. How many moles are in the reactant side? 2. How many moles in the product side? 1. Which has more pressure? Okay, the reactant side has more pressure. 2 moles A and B, 1 plus 1 is 2, versus 1 mole in C. So you increase the pressure, it will go to the side with decreased pressure. Which side has decreased pressure? This is going to shift to the right. Okay. In other words, it's going to shift to the side with less number of moles. Okay, it's going to shift to the side with less number of moles. And in this example above, that's the product side. In this example above, that's the product side. All right, if we increase the pressure, we can do the opposite. What is the opposite of increasing pressure? Let's say we decrease the pressure. Okay, what's the offset of decreasing pressure? Increased pressure. So which side will have increased pressure? Left or right? The side with 2 moles or the side with 1 mole? Okay, so if we decrease the pressure, okay, the reaction will shift to the side with increased pressure. So which side has increased pressure? The one with 2 moles or 1 mole? Okay, so this is going to shift for this reaction, it's going to shift to the left. Okay, it's going to shift to the side with more number of moles. Okay, and that's what we see here. Anybody remember Boyle's law from Chem 1? Boyle's law, one of the gas laws. I think I had you last year. Remember Boyle's law? So if you increase the pressure, what does that do to the volume? Let's say hey class, we're not going to meet here, we're going to meet in the closet. Okay, is that more pressure? Yeah. Yes, okay, you're like shoulder to shoulder. What happened to the volume? Here to the closet is the same volume? Oh. What happened to the volume if we move class from here to the closet? So increasing pressure is the same thing as decreasing volume. Okay, this is because of Boyle's law. Boyle's law. Okay, so increasing the pressure is the same thing as decreasing the volume. Okay. This is the same. Okay? Because if you increase the pressure, how can I increase the pressure in this room? I can increase the pressure in this room by taking class and putting us and teaching you in the closet where the volume has considerably shrunk, where we're literally shoulder to shoulder. Okay? So decreasing volume and increasing pressure are the same thing. Okay, decreasing volume and increasing pressure are the same thing. What happens if I decrease the pressure? Let's say, class, I'm not going to have lecture here in 214. I'm going to have lecture in the auditorium, 220. 220. Okay, will that be more pressure or less pressure? I think most of you will sit all the way in the back. Okay, and some of you will sit there, some will sit here, some will sit there. I doubt anyone will sit in the front row, close to me. What does that mean? If I decrease the pressure, what else did I do? I increased the volume. So decreasing the pressure is the same as increasing the volume, and that is the situation that we see here. Okay, so if you want to increase the volume, all you do is decrease the pressure. If you want to decrease the pressure, all you do is increase the volume. It's going to be the same thing. Okay, and they will shift to the side with more number of moles. Either increase the pressure, increase the volume, decrease the pressure, shift to the side with less moles. If you increase the pressure, decrease the volume. Okay, this is because of something, one of the gas laws known as Boyle's law. Okay, so these things in orange are one and the same. Okay, Boyle's law. Pressure and volume are indirectly proportional. So low pressure, high volume. High pressure, low volume. Man, these are the same here. Increased pressure is the same thing as decreased volume. Okay, same thing. Alright, so that is Le Chatelier's principle. Okay, if you're talking about gases and you're talking about changing the pressure. Alright, so now let's go to the final thing here, and that is temperature. Okay, that is temperature. This is the final disturbance, change in temperature. Our final disturbance in the equilibrium, we can change the temperature. Okay. This is disturbance number 3. Okay, disturbance number 2 is changing the pressure of volume for gases. Disturbance number 1 is changing the concentration of the reactants or products. right, do you guys remember from Chem 1 exothermic versus endothermic reactions? Yes, do you remember, Bailey? Yes or no? A lot of confidence there. That's even more confident. All right, so I'll explain this to you. An exothermic reaction releases heat. And this idea known as enthalpy, do you remember enthalpy? Do you remember it, Bailey?
Yeah.
Okay, the enthalpy, which is the heat flow of a reaction. Okay, this is usually in joules per mole or kilojoules per mole. Okay, this is negative. Okay, enthalpy means heat flow. This is not thermodynamics. This is Le Chatelier's principle, but enthalpy tells us whether a reaction will be exothermic or endothermic. So let's say the reaction is exothermic. Is this exothermic? Yes, okay, because it releases heat. Okay. It releases heat like this. Okay, the surroundings get hotter. Okay, if your surroundings get hot and it releases heat, what is the sign of your enthalpy? Positive or negative? I just wrote it here. Negative. Okay, negative means it's an exothermic reaction. So what happens if and the reaction is exothermic, what happens if we raise the temperature? Okay, which way will it go? Left or right? Okay, raising the temperature means adding heat. So if we add heat, which way will the equilibrium go to offset it? Okay, the offset will be to go to the side with less heat. Which side has less heat? Okay, so this will shift to the left. Okay. This is for an exothermic reaction. Okay, what happens if you lower the temperature for an exothermic reaction? Lowering the temperature means you remove heat. The reaction is exothermic, and you're removing that heat. So which way will the equilibrium shift? Okay, the offset would mean go to the side that has the heat. So for an exothermic reaction, that's going to be the product side to the right.
So in exothermic, that has a positive sign, correct? Exothermic reaction is like the enthalpy is positive, correct?
It's right here, negative.
Oh, I'm sorry.
Exothermic. What has a positive one would be endothermic. Literally, exo means outside. You know, exoskeleton, exterior, it means outside. So the reaction is giving heat to the outside. It's giving heat to the product side. Okay, the flip side would be an endothermic reaction. So what would be an endothermic reaction? Okay, what would it be? Okay, it will be the opposite of this. So A plus B goes to C plus D, and where will heat be here? Okay, so these reactions that are called endothermic require heat. Okay, it's part of the reactant. Okay, it requires heat, and the enthalpy for this is going to be positive. Okay, we call this an endothermic reaction. So we're going to do the exact same thing here. If we raise the temperature for an endothermic reaction, where will it go? We raise the temperature, we add heat. Which way will the reaction shift? Okay, shift to product side. And if we lower the temperature for an endothermic reaction, okay, we lower the temperature, that is, we remove this heat, where will the reaction shift? If the reaction is endothermic and we remove heat, okay, if we remove heat and the reaction is endothermic, it's going to shift to the reactant side, to the left. Alright, so this is for an endothermic reaction. Alright, so that is the third disturbance, adding or increasing or decreasing temperature. Alright, finally, if we do a catalyst, nothing will happen. It will neither shift left or right. Okay, so catalyst does not change the equilibrium constant, and nothing happens. Okay, so if you add a catalyst, it will not shift. It will not shift left, it will not shift right. Alright, so we will wrap this up on Tuesday. Essentially, this chapter is done. So we'll just wrap things up. We'll do some touch-ups on Tuesday after the weekend. And then we'll start chapter 15, and we'll also do a little review as well. All right, have a nice weekend. Turn in your chapter 14 homework if you get a chance. All right, I do not know the due date, but turn in your chapter 14 homework.
Yeah, the chapter 14 homework is due March 7th.
Okay, you can turn it in earlier. I'll put